Our target is f sub xy, evaluated at a comma b. Before doing anything else, let us understand exactly what this means. Here, f sub xy means that we already have f sub y, and now we ask how f sub y changes when we move in the x direction. That meaning is written directly in the definition. Look carefully. The y-coordinate remains fixed at b. Only the x-coordinate changes. We move from a to a plus h. Therefore, our immediate problem is to understand the difference. F sub y at a plus h comma b minus f sub y at a comma b. How can we obtain those two f sub y values from the original function f? That question forces our next step. First, focus only on f sub y at a plus h comma b. To understand it, remember the definition of the partial derivative with respect to y. Here, x equals a plus h and stays fixed. We move only in the y direction. So we compare f at a plus h comma b plus k with f at a plus h comma b, divide by k, and let k approach 0. These are the 2 points, a plus h comma b plus k and a plus h comma b. The short vertical arrow shows the y change. Notice that the x-coordinate is exactly the same at both points. Now focus on the other value, f sub y at a comma b. The idea is identical. This time x equals a and remains fixed while y changes. So we compare f at a comma b plus k with f at a comma b, divide by k, and let k approach 0. Our original difference is therefore comparing two vertical rates of change. The small rectangle displays all 4 points. Blue marks the horizontal x change h, teal marks the vertical y change k. Now something important happens. We did not randomly invent delta. Delta is forced on us by our target. The first value we need is f at a plus h comma b plus k. From it we subtract f at a plus h comma b. Together, these first 2 terms form the vertical change at x equals a plus h. Next we subtract f at a comma b plus k. This begins removing the vertical change at x equals a. Finally, we add f at a comma b. The last 2 terms, taken together, give the negative of the vertical change at x equals a. Only now do we package all 4 terms and name the result delta. Why did exactly these 4 terms appear? The first pair generates the vertical change for f sub y at a plus h comma b. The second pair generates the vertical change for f sub y at a comma b. So delta contains exactly the information required by our original target and nothing extra. Now divide delta by h times k. Dividing by k handles each vertical y change. Dividing by h compares those vertical rates while we move in the x direction. That is why delta divided by h times k is naturally connected with f sub xy. We now have delta, but it still contains 4 terms. How can we simplify it? Define g of y to be f at a plus h comma y minus f at a comma y. Why define g this way? Because a and a plus h are fixed. We allow only y to vary. This turns our 4-term expression into a 1-variable problem. At y equals b plus k, g of b plus k is f at a plus h comma b plus k minus f at a comma b plus k. At y equals b, g of b is f at a plus h comma b minus f at a comma b. Subtract the second line from the first. The result is exactly delta, g of b plus k, minus g of b, equals delta. The 4-term expression has now become the ordinary difference of a 1-variable function. That is the simplification we needed. Substitute that new description of delta into our ratio. Look only at the bracketed expression, g of b plus k minus g of b divided by k. It is an ordinary one-variable difference quotient for g. What expression in the previous line makes the mean value theorem useful? Exactly that circled difference quotient. Therefore, the mean value theorem gives a point D between b and b plus k, where the quotient equals g prime of d. So delta divided by h times k equals g prime of d divided by h. Pause here. The first mean value theorem has absorbed the entire y direction into the single intermediate coordinate d. Now we must ask, what exactly is g prime of d? Return to the definition of g. Differentiate with respect to y. We obtain f sub y at a plus h comma y minus f sub y at a comma y. Now substitute y equals d. Therefore, delta divided by h times k equals this difference of f sub y values divided by h. Stop here. Look at the points a plus h comma d and a comma d. Their y-coordinate d is fixed. Only x changes from a to a plus h. So we now have a change of f sub y in the x direction. That observation tells us exactly what function to define next. Define phi of x to be f sub y at x comma d. Why are we defining phi? Our previous line already contains f sub y at a plus h comma d minus f sub y at a comma d. Since d is fixed and only x varies, we simply give f sub y at x comma d a short name. At x equals a plus h, phi of a plus h equals f sub y at a plus h comma d. At x equals a, phi of a equals f sub y at a comma d. Therefore, g prime of d is phi of a plus h minus phi of a. And g prime of d divided by h is the ordinary difference quotient for phi. Again, what expression in the previous line makes the mean value theorem useful? It is the circled quotient, phi of a plus h minus phi of a, all divided by h. Apply the mean value theorem again, now in the x direction. For some c between a and a plus h, that quotient equals phi prime of c. Remember that phi of x is f sub y at x comma d. So, what is phi prime of c? It is the partial derivative with respect to x of f sub y, evaluated at c comma d. In our notation, that is f sub x y at c comma d. Therefore, delta divided by h times k equals f sub x y at c comma d. Now, for the first time, let us show the complete chain. We wanted f sub x y at a comma b. That forced us to examine how f sub y changes in the x direction. To understand those two f sub y values, we needed vertical changes of the original function f. Those vertical changes naturally produce delta, and therefore delta divided by h times k. Writing delta as g of b plus k minus g of b made the first mean value theorem useful. It produced g prime of d divided by h. That expression revealed a change in f sub y with respect to x. Naming f sub y at x comma d as phi of x made the second mean value theorem useful. The second theorem produced phi prime of c, which is f sub x y at c comma d. That is the chain. None of the steps was chosen randomly. Every step created the need for the next step.